it and talk about water, okay, and see how water can ionize. So pure water also can undergo self ionization, okay, as follows. So you have your pure water, okay, so it will undergo self ionization to produce hydrogen ions. Sorry, this is half arrow. To produce hydrogen ions, aqueous, and the OH ions. And this is also aqueous. This is a liquid. So let's make this half arrow. This is a half arrow. Okay. So this is half arrow, half arrow. Now from this expression, we can determine the Kw, the ionization constant of water, which is the concentration of hydrogen ions, not so, plus times the concentration of OH ions minus everything out of the concentration of water. The concentration of water. But now remember, water here is a solvent, or this is water that is ionizing. So water being a solvent, it means the concentration of water or water is in large excess. Large excess. So therefore, it is assumed that its concentration in this case, okay, it tends to unity, which is 1. So therefore, if we substitute, then the expression for Kw, the ionization constant of water, is simply the concentration of hydrogen ions, okay, at equilibrium times the concentration of OH ions at equilibrium. Now, if you know the Kw, you can determine the concentration of hydrogen ions. If you know that, you can still also calculate the concentration of OH ions, because still at equilibrium, the concentration of OH is equal to the concentration of hydrogen ions, okay, which is equal to 1 times 10 power negative 7 moles per decimeter cubed at room temperature, okay. And so when you substitute this, then you can get Kw, okay. We can get our Kw, and our Kw is simply the 1 times 10 times 10 power 7 10 power 7 squared, because since the concentration is the same, so we can simply either substitute here hydrogen and it becomes squared, or OH and it becomes squared, okay. And so if you get this out on your card, you get our Kw. And what's the Kw? It is 1 times 10. Since it's powers, we shall just multiply powers. Times 10 power negative 14 mole squared decimeter 6. Let me write it here. It's 1 times 10 power negative 6 power negative 14, okay, which is, sorry, the units, it is mole squared decimeter minus 6. Where are we getting it from? We have gotten the moles per decimeter cubed. Let me write it somewhere here. Moles per decimeter cubed times moles per decimeter cubed. And so what do you get? You get mole squared decimeter power negative 6. Now, how is this applicable? This is applied in cases where we determine pH and the pOH of any solution. And so let's first see what pH is. pH is simply the negative log to base 10 of hydrogen ions, or to the concentration, in fact, not just simply hydrogen ions, but to the concentration of hydrogen ions in a solution. So given any solution, let's say the solution of water that we have. Okay, leave water. Given any solution, maybe the solution is maybe a monobasic acid, okay, AH or HA. If you dissolve this acid in water, it will ionize partially to give us the hydrogen ions, okay, aqueous, and the A ions. A ions also aqueous. Now at equilibrium, we can determine, if you know the Kb of that acid, we can simply determine the concentration of hydrogen ions, okay, which is simply concentration squared out of the undissociated acid. Not so? Undissociated acid, Ha. So therefore, our concentration of hydrogen ions is simply, if you know this at equilibrium and you know this at equilibrium, then it is simply the square root of Kb times the concentration of undissociated acid. Now, if after getting the concentration of hydrogen ions, then your pH, which is potential hydrogen pH, is simply the negative to the log of base 10 of concentration of hydrogen ions in that solution. So if you know the concentration, then you simply substitute to this and you go to your calculator and get the negative log of concentration of hydrogen ions that you have gotten here, and you get the pH. And the pH will usually range from 14, okay, downwards, and it can even be negative. You can have negative pH. Let's talk about the pH of water and see how is it. Now you know pure water contains the same concentration of hydrogen ions and hydroxyl ions, right? Yes. And from the Kw of water, you remember how we got in that expression? It is concentration of hydrogen ions, okay, from that expression, times concentration of what? Of OH ions, okay? And the Kw is 1.0 times 10 power negative 14. That's our Kw. And we have calculated it, you saw. The concentration is equal, so even if I substitute the concentration of OH is at equilibrium is equal to the concentration of hydrogen ions. So I'll simply substitute this with hydrogen ions. And if I put it here, it will be squared. Not so? So our concentration of hydrogen ions squared should be equivalent to the Kw. So take the square root, you get the concentration of hydrogen ions in pure water as 1 times 10 power negative 7 moles per decimeter cubed. Now, if you know this, after getting the concentration of hydrogen ions in this solution, then we can use it to determine the pH, which is the potential hydrogen, as negative log to base 10 okay, of concentration of hydrogen ions. So simply substitute. Our pH is going to be negative log, okay, of 1 log to base 10 of 1 times 10 minus 7, and you get your answer as 7. So the pH of pure water therefore is 7. That's why water is said to be neutral. 7 is neither acidic nor basic. It is simply neutral. And pure water must be neutral. Not so, guys? Yes. Let's see how we can get pure pH of acids. Consider, for strong acids, they simply ionize. Okay? They ionize fully. Take an example of HCl. Okay? Which ionizes fully to produce hydrogen ions and chloride ions. If you have a 0.1 molar HCl, you produce 0.1 molar hydrogen ions and 0.1 molar chloride ions. So the pH fully depends on the concentration of hydrogen ions. And so it doesn't require a lot to determine. It simply substitute the concentration and you get the pH. But now, for weak acids, okay, we have that example. For example, the pH of a 0.02 sulfuric acid. This one is a strong acid, so it fully ionizes. So the pH is simply negative log to base 10 of 0.02 molar sulfuric acid. And the answer is going to be the pH. But now for weak acids, you can do that example, but this is simple work. Okay? It is simply substituting it to ionize. Anyway, you do this. Do this. Actually, there's something I've not told you. Now for sulfuric acid here, let me first tell you something and then you do. Now for sulfuric acid, it will ionize fully to produce 2 moles of hydrogen ions, okay, and 1 mole of sulfate ions. And so what does that imply? If you have 0.02 molar solution of sulfuric acid, you produce 2 times 0.02 molar concentration of hydrogen ions. So the pH therefore here is simply negative log to base 10 of 0.04. And what you get is supposed to be your answer. And pH has no units because it's a logarithm. Okay? You're not supposed to put any units. So similarly, you can do that and it's very easy. And I feel we shouldn't take much time doing this. Yes, yeah, thanks for that good work. So we shall do just for this. So for sulfuric acid, like we said, being a strong acid, it will fully ionize aqueous to produce fully. Here we even use 4R to produce 2 moles of hydrogen ions aqueous plus sulfate ions 2 minus aqueous. So if you have 0.025 molar sulfuric acid, it means it will produce 2 times 0.025 molar sulfuric acid. So the hydrogen ions. So therefore for our pH, by the pH it is written as small p and then capital H. So our pH is going to be negative log to base 10 of, I think this is 0.05, 0.05, and somebody said the answer was 1.3. No units, don't put units. Is it 1.3? I guess so. Yes, that's good. Let's see, how about for weak acids? Weak acids don't fully ionize. They partially ionize. So you cannot easily tell the concentration of hydrogen ions in that solution. But if you know that Ka, the dissociation constant, or if you know the initial concentration, and the degree of dissociation, by the way, then you can easily determine the concentration of hydrogen ions in that solution. So you can consider such an acid, for example, ethanoic acid, which is a weak acid, COOH, okay, that will partially ionize to give us ethanol with ions, okay, and OO ions, or ethanol with ions, and hydrogen ions, aqueous. Now, initially at T equals 0, you have C of ethanol with ions, but you would have 0 of ethanol with ions, C of ethanoic acid, 0 of ethanol with ions, and 0 hydrogen ions. But at T, at equilibrium, if you form, maybe, let's use the ionization constant, but you can also use Ka, depending on what is given. If you have the ionization constant under C, we shall form alpha C. And remember that alpha C is our degree of ionization. Our alpha is our degree. And also form alpha C, okay, of hydrogen ions. And so if mole ratio 1 to 1, it means, or it implies that alpha C of the acid has dissociated. So the undissociated acid is C minus alpha C. So from Ka, which is equivalent to, now you don't even need to use Ka here. You know the alpha, which is the degree of ionization, and you know the initial concentration. You can determine the concentration of hydrogen ions. And the concentration of hydrogen ions in this case is going to be simply alpha C, which is the degree of ionization times the initial concentration. And then after getting the concentration of hydrogen ions, then you simply find the pH, which is equal to negative logarithm to base 10 of concentration of hydrogen ions. And you have the pH, as simple as that. Now, how about if you are given Ka and initial concentration? You can still determine. If you are given Ka and the initial concentration, you can still determine from this COOH, okay, I won't write the units. You have C and then CH3 COO minus plus the hydrogen ions. I want to write the units. At T equals 0, initially you will have C and 0 ethanoate ions and 0 hydrogen ions. But at equilibrium, then if you form X, you don't know the concentration of hydrogen ions. You also don't know the concentration of ethanoate ions. If you form X and from mole ratio which is 1 to 1, then it means X of the acid has dissociated. So what will be the concentration of acid that remains? It is simply C minus X. Okay? So from Ka, we can determine the concentration of hydrogen ions squared. Why am I saying squared? Because it is all X out of C minus X. Okay? Yes. So if you take this side, it will be Ka minus Ka times C minus X. Ka times C minus X. It should give us concentration of hydrogen ions squared. But since this one is a weak acid, the C minus the X is negligible. Okay? It is equivalent to C. Because this is a weak acid, so its ionization is very weak. That the X, which is the degree, is really. So that we can get our concentration of hydrogen ions from simply Ka times C. And so after getting the concentration of hydrogen ions, we can substitute in our formula for pH, which is simply negative log times negative log to base 10 into concentration of hydrogen ions. And we have our answer. So you can do that. So we have an example here. We have our ethanoic acid, and we have the initial concentration, and we have the Ka, and the question wants the pH. So from the concentration of hydrogen ions, which is simply the square root of C, which is 0.01 times Ka, which is 1.8 times 10 power negative 5. So you get the concentration of hydrogen ions in mole per decimeter cubed. And then from this we can get our pH as negative log of the concentration. So what's the answer here? The answer is 4 point. Your voice is so down.
4.2.
4.2. Your voice is so down.
4.2.
4.2. Simply that times 10. Times 10 power.
4.2.
Okay, someone is saying that the answer is 1.10, 1.8, 1.8 times 10 power negative 7 moles per decimeter cubed. And so when we substitute 1.8 times 10 power negative 7, what is the answer? What is the answer? The pH is, you can drop it in the chat box. I'll find it. Let me find the answer. So somebody is saying that the answer is 6.8. 6.8. And pH has no units. Don't put anything. pH doesn't have unit. It's a rock. So you do that and we call it a day.